Plenary lecture number 21 by János Pach from Alfred Renyi Institute, Budapest, Hungary. And I invite Professor Bapat to chair this session. Professor Bapat.
Thank you. I'm pleased to welcome you all to this session. The speaker for this session is Professor János Pach. So Professor Pach is research advisor at Renyi Institute, Budapest, and head of the Laboratory of Combinatorial and Geometric Structures at MIPT Moscow. His main fields of interest are discrete and computational geometry, convexity, and combinatorics. He wrote more than 300 research papers. His books, Research Problems in Discrete Geometry with Brass and Moser, and Combinatorial Geometry with Agarwal, were translated into Japanese, Russian, and Chinese. He is co-editor-in-chief of Discrete and Computational Geometry and serves on the editorial boards of 10 other professional journals. For his scientific achievements, he received several prizes, including the Lester R. Ford Award of the Mathematical Association of America 1990 and the Renyi Prize, and the Academy Award from the Hungarian Academy of Sciences in 1993 and 98. He was elected ACM Fellow in 2011, member of Academia Europaea in 2014, and AMS Fellow in 2015. He was invited speaker at the International Congress of Mathematicians in Seoul in 2014, and is plenary speaker at the European Congress of Mathematics in Porto Rose in 2021. So today he will speak on low-dimensional combinatorics. So I welcome Professor Pach and request him to give his lecture.
Thank you very much for the kind introduction. First of all, I also want to thank the organizers for inviting me. Although I am heartbroken that I cannot be there in Cochin in person. I was there 10 years ago when there was a satellite event to the International Congress. And I was very much hoping that until the bitter end, until the last moment, that I will be able to return this December, but it didn't materialize. Now, so there is a question mark here, low-dimensional combinatorics. So I like to outline some kind of a subject or a possible subject. We'll see if such a subject exists. But before that, I'd like to show this picture of the way how I pronounce it is Pahayappa's college in Madras. So this is one of my entitlements, you see, why to speak here, because the first 4 letters of the name of the college actually happen to be my name. But I am afraid that it's more Pachayappa's college anyway. So this is the college that was attended by Ramanujan. Of course, he excelled there in mathematics, but ignored all the other subjects. So it wasn't a success story, but in some sense, this was very helpful, because this is why he decided to pursue his life as an independent mathematician, and the rest is history. So very few people know that he was also interested in geometry. So this is a way how he constructed square root of pi, or an excellent approximation. I don't think that there is any other approximation that comes close to it. It's tied to the eighth digit, and geometry is in the background of sort of the topic of my talk. So what I would like to start with, so it's low dimensional. I have to explain what I mean by low dimensional, but I really won't explain it very clearly, or I should say I will explain it by examples. So one of the big problems with combinatorics and also computer science and statistics and whatever, that as the dimension grows, somehow things become very difficult. Combinatorists often call it the combinatorial explosion. And there are some ways, so this is basically the idea or the philosophy of this talk, is that one can actually make problems easier and try to solve them under a condition that we restrict the dimension of the problem to some bounded range. Of course, the question is that what kind of dimension we use, and there are several dimensions. There is the natural one, the Euclidean dimension, 2, 3, 4, whatever small dimensional spaces, and we try to put our combinatorics problems in that range. But there will be other notions of dimensions, algebraic notions, also combinatorial notions like the Vapnik-Chervonenkis dimension. So let's just jump into it and start with the first problem. So if everything goes fine, then I will be able to mention 4 problems and how it helps to consider bounded dimensional variants of these problems. Also, I'd like to ask the president to sort of tell me 5 minutes before I am supposed to finish that. I'm supposed to finish so that I can wrap up. So the first problem, famous problem in combinatorics, the independence number of graphs. So what is the independence number of a graph? The maximum number of vertices you can choose in the graph so that no 2 of them are connected by an edge. So here in this graph, if you look at these 4 vertices that are marked, they form the largest subset so that there is no edge between them. And we know that this is a famously difficult NP-hard problem to determine the independence number of a graph. In fact, it is very difficult in a strong sense, because even to approximate it by within a factor of n to the 1 minus epsilon, n to the 0.99. Well, to approximate the independence number with a factor of n is trivial, because the independence number is a number between 1 and n, if n is the number of vertices on the graph. So with an error of n, you can definitely, multiplicative error, you can estimate it. But if you want just an error which is n to the 0.99, then it's impossible to estimate it efficiently, which means in computer science in polynomial time, unless p equals mp, that really no one believes. Now, let's try to consider a geometric instance of this problem, and this instance is intersection graphs. So intersection graphs, the idea is the following. The idea is on the picture. So you take some geometric objects, in this case, for instance, these green strings. I don't know if you can see this little hand, my mouse. So you have these 5 green strings in the plane. Each of them you represent by a vertex of the graph. And 2 vertices like 1 and 2 you connect by an edge, because the corresponding 2 curves, 1 and 2, they intersect. In this way you get an intersection graph of these curves, the intersection graph of these green strings, which Ron Graham called the string graph, the intersection graph of strings. He popularized the problem of looking at the structure of string graphs among mathematicians. The definition, however, doesn't come from mathematicians. It comes from very clever people. For instance, I think that the first one who considered that was Seymour Benzer, who was a molecular biologist who also got the Wolf Prize and many other prizes, very clever person. So he considered segments of chromosomes, and in his research, these graphs played an important role, and he even formulated some very sound mathematical problems about them, which are really the problems with which mathematicians and computer scientists fought for a long time. And shortly after, 7 years after, Frank Sinden, who worked at Bell Laboratories, this is the connection because at that time Ron Graham also worked there, sort of introduced the same definition in relation to printed layers, VLSI design. And later again, somehow, John O'Keefe, who got the Nobel, neuroscientist who got the Nobel Prize in biology, he also considered the same definition, and they made some very interesting mathematical observations, especially Sinden, who proved interesting things. Okay, so let's just restrict our attention to string graphs, and then let's see if we can say anything better. So for the purpose of this talk, I will only consider k-intersecting string graphs. So this means that that intersection graphs of strings in the plane, these green things, so that any 2 of them intersect in at most k points. Like here, these 2 strings intersect in at most 3 points. And for them, actually, we can prove much better. We can prove that we can approximate for any little epsilon you want. We can approximate the independence number of an n-vertex string graph up to a factor of n to the epsilon. So not only n to the 0.99, but n to the 0.00001. We can do it in polynomial time. And even we can exactly determine the independence number of an n-vertex string graph in time 2 to the n to the 4/5, which may look ridiculously high, but actually it is ridiculously high. But of course, it's better than the trivial 2 to the n, right? Because if we look at the graph and we consider each of the subsets of the vertices, each of the 2 to the n subsets of the vertices, and by brute force, of course, we can find which one is an independent set, and so to have such an ugly piece trivia, this is better. So what's the reason? Why are string graphs better? What is the blessing that comes together with restricting the geometric dimension of the intersection graph to the plane? So the blessing, at least if we do it in the plane, is that in the plane we have a separator theorem. Actually, there are other separator theorems which also generalize to higher dimensions and other dimensions, but But the simplest form of it, the seed of it, all of them go back to the idea of Lipton and Tarjan of the planar separator theorem, which everybody knows, or if you don't know, then here is a picture that shows this. So if you look at the usual grid, square root n by square root n grid, it has n vertices and something like 2n little edges. So we can separate the vertices of this graph, or we can separate this graph into two actually equal parts, so that we delete only square root n of the vertices, this layer in the middle. And in general, it is true, but by deleting at most 2 times square root n vertices, we can disconnect any planar graph, not just this one, but any planar graph, into 2 disconnected parts, so that each of the parts contains at least 1/3 of the vertices, 2 roughly equal parts. Now, there is a related theorem which is true for string graphs, which is not very surprising, because if you think about it, if you look at the string graphs, well, it's not a graph yet, because you just have, if you look at the geometric picture of the strings, then that is not a graph yet, but you can introduce vertices at the intersection points, and you can turn it into a planar graph. At any rate, what the theorem says, what one can prove for string graphs, and this was proved in several installments between 2010 and 2017, that if you look at the string graph which has e edges, so what does it mean? An edge of a string graph is a pair of strings that intersect. So if there are e pairs of strings that intersect, then we can separate the graph into 2 disconnected parts. This means that we can color those strings, if you wish, by 2 colors, so that each color class contains at least 1/3 of the strings, by the removal of only square root e strings. And then there is absolutely no relationship between the red strings and the blue strings. So it's in spirit, it is similar. Really, it is related to the original Lipton-Tarjan theorem, but there's a big difference. So here we delete square root n vertices. Here we delete square root e vertices, but e is the number of edges, not the number of vertices. So this is this theorem is much more complicated than the Lipton-Tarjan theorem. For the proof, one needs multi-commodity flows, some deep theorems of metrical deformations by Burgen, and results about crossing numbers. So this is the trick. This is the engine, the sort of inductional engine that is behind, you know, behind the phenomenon that we can approximate independence numbers of strings so much better than independence numbers of other graphs. Now, I will come to the second problem, but before of that, I have to remind you of these 2 standard notations in graph theory. So if you have a graph, then chi of g is the chromatic number, minimum number of colors you need to color the vertices, so that no 2 vertices of the same color are connected by an edge, and the clique number, maximum size of a clique, of a complete subgraph in the graph. Of course, if you have a clique of size omega, then any 2 vertices of this clique require a different color, so that chi of g is larger than or equal to omega. And as we know, this is by no means reversible. There are graphs in which the chromatic number is much, much higher than the clique number. And the simplest examples found by Michalski, graphs in which the clique number is 2. This means that there is no triangle, but the chromatic number can be arbitrarily large. And as we know, here I put here a theorem of Erdős that shows that much, much more is true. So in general, this is a basic question in graph theory, that what is the relationship between these two important graph parameters. Now, there is a very useful concept, very useful idea, which was introduced by Gyárfás, and also partially by Gyárfás and Lehel. By the way, you don't have to read all these things that are on this slide. I will tell whatever is worth reading. So what was Gyárfás's idea? Okay, it's not true that that in general for a graph the chromatic number is equal to the clique number, but for some interesting graphs, perhaps it is true that the chromatic number of the graph can be bounded by a function of the clique number. So, you know, graphs in which these two numbers, the chromatic number and the clique number, are equal, they are the perfect graphs. So you can think of those graphs as nearly perfect. Now, Gyárfás called them chi-bounded graphs. So it's reminding us that chi, the chromatic number, is bounded by a function of the clique number. And it turns out that many geometrically defined examples, like intersection graphs of rectangles, where the vertices correspond to rectangles in the plane, axis parallel rectangles, two of them are again connected by an edge if the corresponding rectangles intersect. They are a chi-bounded family. Actually, it was proved before Gyárfás came up with this definition. And Asplund and Grünbaum proved that in fact the chromatic number can be bounded by the square of the clique number. Today we know much better. We know that was a recent advancement that in fact chi can be bounded by omega log omega. We still don't know if it can be bounded by a constant times omega. And similar results are true for intersection graphs of Boas, or not only intersection graphs, but disjointness graphs, which are complements of the intersection graph, where two geometric objects we connect by an edge if they are disjoint. So for instance, disjointness graphs of segments, they are chi-bounded. But there are a number of similar intersection graphs which are not chi-bounded. Already Berling, who was a student of Grünbaum, noticed that, for instance, if we consider intersection graphs of three-dimensional boxes, then three-dimensional axis parallel rectangular boxes, then it's not a chi-bounded family. So usually it's not easy to decide whether for a family of graphs, whether this family is chi-bounded, whether those graphs are nearly perfect in the sense of Gyárfás, let alone the problem that assume you prove that there is such a binding function f. What is the best function f for the family? That's usually a hopelessly difficult task to determine. Okay. So we have seen that that we haven't seen, but it is true, that if you consider disjointness graphs of strings, again, strings are just continuous curves in the plane, then and to each of them we assign a vertex. If two are disjoint, then we connect them by an edge. These graphs are not chi-bounded. Nevertheless, we can say something if we restrict our attention to X monotone curve. So an X monotone curve is just a curve like a graph of a function, right? Which means that every vertical line, they are continuous curves, and every vertical line intersects them in at most one point. So if you have a complicated spiraling curve, then it's not X monotone. It doesn't go from left to right. So X monotone curves are special. And it turns out that, that the disjointness graph system of X monotone curves, it is already chi-bounded. So with this assumption, actually chi can be bounded from above by the fourth power of omega. And it was open for a long time whether this bound is close to being optimal. No one really believes that it is, that it was optimal. There is a very elegant proof of this fact, which follows by using Dilworth theorem, or rather the dual of Dilworth theorem, 4 times, but it looks like just an attribute of the proof that we have to use it 4 times and not 3 times. So what is an optimal bounding function? To our greatest surprise, last year, István Tomon and myself managed to prove that actually this omega to the 4th is essentially tight. It is so much essentially tight that I believe that one can even determine the right constants here. So the question is that why this is true? Why can we give in this particular case a reasonable, almost tight bounding function, which bounds the chromatic number in terms of omega. So before I make a comment about it, or I sort of outline why it is true, I'd like to make a comment. Actually, we don't have any better upper bound for the chromatic number of disjointness graphs of segments than omega to the 4. And we have no idea whether this omega to the 4, if we restrict our attention to disjointness graphs of segments, it is the best possible. In fact, we are almost convinced that it is not, that a much smaller bounding function would apply to this case, even omega square or something like that. But we don't know. Okay, so why can we prove this result? Well, the reason for that is the following. We further restrict our attention from these X monotone curves, X monotone strings, to grounded X monotone curves. This is a technical restriction, so the difficulty of the problem already appears if we look at this collection. So, however, what are grounded? All of them start on the y-axis. So each of these curves starts at the y-axis and goes to the right, and they are X monotone. They don't turn back. These are grounded. And if they are grounded, then we can order them according to their left endpoints, right? How high their left endpoints are. So this is A is the smallest one, lowest, B is the second smallest, C is the third smallest, D is the in this picture. So we look at a disjointness graph of such grounded X monotone curves, and we call it a semi-comparability graph, ugly name, but you will see from the definition why this is the right name. If whenever you take 4 elements, A, B, C, D, 4 of these strings, 4 of these green curves, A, B, C, D, which follow each other in this order, and A, B, B, C, C, and C, D are edges. This means that of the disjointness graph. This means that the curve A is disjoint from the curve B. B is disjoint from the curve C. C is disjoint for the curve D. Then it follows. One can check very easily on the picture that in that case either AC or BD are also edges. So either A and C are disjoint or B and D are disjoint. So assume that A and C are not disjoint, like here, they intersect each other. But B and C were disjoint in the disjointness graph. So if B and D intersect each other, if BD is not an edge of the disjointness graph, then somehow B is supposed to, D must intersect C, this intermediate curve. So this we call a semi-comparability graph, because in a comparability graph, you see if A, B, and BC are edges, this means A smaller B, B smaller C, then A is smaller than C, so AC should be an edge. And if BC and C is B smaller than C, C is smaller than D, then B is also smaller than D. Both of them should be edges. In this case, only one of them is an edge. So this is a semi-comparability graph. If you have a comparability graph, if both of them would be edges, the comparability graphs are perfect. So for them, everything is nice. The chromatic number is bounded by the clique number. For semi-comparability graph, we still have a bound. This is the essence of the thing. And this bound is not omega, but omega plus 1 choose 2. And this is tight. So this is in fact, the tightness is difficult to prove. So this is why we can do better for disjointness or intersection graphs of curves. Again, the geometric dimension is bounded. Okay. Now, in order to mention the third problem, I have to look at, I have to recall Ramsey's theorem that everybody knows, which is uses these two important parameters, the clique number and the independence number of the graph. So what Ramsey's theorem says in the formulation of Erdős and Szekeres, quantitative formulation, is that if you take a graph with n vertices, then it contains either a large clique or a large independent set. One of these two parameters, omega or alpha, is large. How large? At least log of n, logarithm of n. And what Erdős and Vrényi suspected Erdős and Hajnal suspected for a long time that for many interesting families of graphs, actually you can have a much better Ramsey theorem. Instead of the logarithm of n, you can find a clique or an independent set of size n to some constant, which depends on the family. So here is a picture from the 1960s with a young Hajnal, 30-something, and still very young looking, but not so young, Paul Erdős, who is about 50. So what is the Erdős-Hajnal conjecture? So the nicest way of formulating it is perhaps to formulate it for hereditary properties. A hereditary graph property is that if a graph has the property, that every induced subgraph of it has the property. For instance, if a graph does not contain C5 as an induced subgraph, then the same is true for any induced subgraph of it. This is a hereditary property. Intersection graphs of segments or strings, string graphs, also a hereditary property. If a graph is an intersection graph of segments, then if an induced subgraph induced by a subset is an intersection graph of the corresponding segments. And what Erdős and Hajnal conjecture is that if you have a hereditary graph property, which is not trivial, so not true for every graph, then for them, for any such property, there is a positive constant, so that every graph is n vertices which has this property, has a clique or an independent set of size n to that constant, which is much better than the logarithm of n. So they could prove something. Actually, they could prove that instead of n to the constant, instead of e to the c log n, they could prove that there is always a clique or an independent set of size e to the constant times square root of log n, which is already a non-trivial result. Now, in this area for the Erdős-Hajnal conjecture, there were dramatic sort of developments in the last couple of months. For instance, last week, this was one of the oldest problems here. Last week, Chudnovsky, Scott, Seymour, and Spirkle proved that the Erdős-Hajnal property is true for our first example, for the family of graphs that don't contain C5 as an induced subgraph. And for this last example of string graphs, intersection graphs of strings, it was also a dramatic development that István Tomon, a couple of months ago, proved that the conjecture is true. So I would like to show you another example. This example requires introducing a definition, but I am not giving this definition in precisely. So what is a semi-algebraic graph of bounded complexity? So a semi-algebraic graph of bounded complexity is a graph whose vertices you can embed in a bounded dimensional, d-dimensional Euclidean space, so that if you consider two vertices, which correspond to 2 points in this d-dimensional space, then whether or not those 2 points are connected by an edge can be decided by a bounded number, say at most d, polynomial equations and inequalities of degree at most d. So that those are semi-algebraic graphs. And so anything that you can define in terms of algebraic equations is like intersection graphs of segments, clearly to decide whether two of them intersect, where you have to know the coordinates of the endpoints of it. And then there are some polynomial inequalities that will decide that. Unit distance graphs, things like that, they are all semi-algebraic graphs. And there is a relatively old theorem of Alon and company, where we prove that semi-algebraic graphs of bounded complexity, which is also a hereditary property, they also have a clique or an independent set of size n to the constant. So the Erdős-Hajnal conjecture is also true for them. Okay. Now, so what is, so I don't want to give a hint for that, but what I like to say is just to mention that what is the blessing, what is the thing that we can do with semi-algebraic graphs. For semi-algebraic graphs of bounded dimension, we have the d-dimensional Euclidean space. And there are all kinds of things in the d-dimensional space that we can do just because of the geometry. And one of the things, the particular thing that we use is the cutting lemma or Chazelle or Friedman. So you don't have to read exactly. I will send my slides, so later you can check the technical statement. But this picture here, it sort of summarizes the essence of this thing. So what this picture, in this picture, what you see is there are some surfaces. In this case, some curves. These curves here happen to be lines. Then we can divide the space into a small number of simple pieces, in this case, these little squares, so that essentially all of them are intersected by roughly the same number of surfaces or same number of curves, same number of lines on this picture. So there is a regular partition with respect to the system of surfaces of the space. This is what saves us. And now this is the final part of my talk. Vapnik-Chervonenkis dimension, also a dimension notion. So we say that if you have a family of sets or hypergraph, if you wish, then a subset of the ground set A is called shattered by them. If you take any subset of A, any B, there is an hyperedge, there is a set in the family which will intersect A in exactly this subset. So there is a set A, it's called shattered. If for all of the, if A has k elements, then all of the 2 to the k subsets of A, there is a set which will carve out exactly this subset from set A. And the Vapnik-Chervonenkis dimension of the family is the size of the largest set A which is shattered by the family. So there are many geometric examples of that. One example is semi-algebraic set. So if we look at points in the d-dimensional space and we consider those subsets, those hyperedges, if you wish, that are carved off by a semi-algebraic set of bounded complexity, they are bounded in C dimension. This is not difficult to prove. And the most important property is this first one. This is the important blessing here, which is usually called Sauer's theorem. That if we have such a family whose Vapnik-Chervonenkis dimension is D on an n-element set, well, in general, if you have a hypergraph, a set system, it can have 2 to the n. At most, it can have 2 to the n subsets. But only at most the sum of the first binomial coefficients, first D binomial coefficients, the order of n to the D is the number of subsets if we assume that the Vapnik-Chervonenkis dimension of the set system is small. So small Vapnik-Chervonenkis dimension means that there are few subsets. And I have to define a graph of bounded Vapnik-Chervonenkis dimension. A graph of bounded Vapnik-Chervonenkis dimension is I look at the vertices of the graph, I look at the neighborhoods of the vertices, they form a set system, and if that set system has small dimension, then the graph has small Vapnik-Chervonenkis dimension. That's the definition. And if we bound the Vapnik-Chervonenkis dimension of a graph, then where we cannot quite prove the Erdős-Hajnal conjecture that 2 to the constant times log n, we can find a Krikhoren independent set of size. This is n to the c in another form. But apart from a little or one error in the exponent, we can prove that. And so I will finish my talk here because my time is up. I just want to say that one can also explore bounded Vapnik-Chervonenkis dimension for the sunflower problem, which many people know because recently there has been several breakthroughs with respect to that, the Erdős-Radó sunflower problem. If you assume that we restrict our attention to set systems of bounded Vapnik-Chervonenkis dimension, then Andrew Sook, Jacob Fox, and myself can again almost prove the Erdős-Radó sunflower conjecture. But this is another story. So thank you very much for your attention, and this is a good time to stop with this beautiful picture.
Yeah. Are there any questions or comments from the audience? You can unmute and ask directly if there are any questions.
Well, if you later have any questions, you can always send me email. I will be happy to answer.
Okay, so since I don't see any questions, I think let us thank Professor Park for a very interesting talk. Thank you very much.
Thank you very much.
Thank you, Professor Bapat and Janos. We will reassemble at 5:30 for a plenary talk by Boyan Mohan after 30 minutes.